back to CCAI321 Artificial Neural Networks. So let's go through an example of a practical application of convolutional neural networks. And in this example is an implementation of using convolutional neural networks on the handwriting data set of the digits from 0 to 9. So the data set itself comes from MNIST, and the data set looks kind of like this. These are different images in this data set, and the challenge, of course, is to be able to classify an image into one of the 10 different digits between 0 and 9. Each image is 28 by 28 pixels in size. Each image is a grayscale image, which means it has a single channel, has a depth of only 1. There are 10 target classes representing the digits from 0 to 9. And you can start here by installing TensorFlow and NumPy and downloading the MNIST dataset using pip and Python. You can open an empty Python file and start by importing these packages into your script. So NumPy as np, import the dataset, and import Keras from TensorFlow. Step 1 is to load the training and test images and their labels. So that's done with these 4 lines of code: training images, training labels, test images, test labels put into these 4 lists. Print out the size of these data sets. So the training images there are 60,000 of them. Dimensions are 28 by 28, like I said. The corresponding labels have to be of equal number, 60,000. The first step is to normalize the images so that the pixel values are in the range minus 0.5 to 0.5. You can do that by dividing by 255. That reduces the range of values to 0 to 1, and then subtracting 0.5, and that changes the range of values to minus 0.5 to plus 0.5. You have to reshape the images, add a third dimension. Now that's because the Keras, the library that you're using in here, requires a third dimension, even if the data is only 2-dimensional. So you can do that by using the expand dimensions function that NumPy provides, and you have to provide the axis along which that expansion is to take place. Following that, you can use the sequential command to set up your convolutional neural network. Define the number of filters to 8, filter size to 3 by 3. Define the pooling size to 2 by 2. Shape of the input is 28 by 28 by 1. For the pooling layer, you're using the maximum function. So this is a max pool layer that you have, and the output is provided via a softmax layer, and the number of output classes is, of course, 10. Types of layers you'll be using will be a 2-dimensional convolutional layer, a fully connected layer, a flattening layer, and a max pool layer, 2-dimensional. Flattening is the step of taking two-dimensional data and basically like a two-dimensional array in this case, and just putting it, converting it to a one-dimensional array and treating it as such going forward. So these are the basic steps happening. You have the input image, 28 by 28 in size, form convolution, pooling to reduce size, flatten it, meaning convert it to one-dimensional array, add a fully connected layer in between, and then you have your output. Then you have the softmax output layer. In this case, we have not just 1 to 4, but 1 to 10 different classes at the output. For this specific example, input will be 28 by 28. Convolution by a 3 by 3 filter will make that the output from that layer, from the convolution step, will be of 26 by 26 by 8 in dimension. We've got 8 different filters, so that makes for like a 3-dimensional output. Max pool reduces the dimension to 13 by 13 by 8. Remember this, the depth has to stay the same, and this is passed to a softmax layer, which will give you confidence values for which of these 10 different classes the input belongs to. And all of that is described in here in this sequential command. For compiling the model, you have to specify the gradient-based optimization function. In this case, it uses something called an Adam function. You have to specify loss function. This one uses something called a categorical cross entropy function for its loss function. And for the metrics to report, it specifies to report accuracy. More on accuracy a little later. When we have multi-class classification, when we're working on a multi-class classification problem, we usually use a categorical cross entropy function as a loss function. For binary classification problems, the binary cross entropy loss function. You can specify how many times you want the training data set to run through the network, and that number is called an epoch. Here we specify the number of epochs to be 3. So basically, each entry in the training set will be used 3 times to train the network. For validation data, of course, we have test images, and we provide that as our test data. Now, in a multi-class classification problem, you can have multiple classes, such as we have 10 different classes, but for simplicity, you can assume we have a classifier that assigns inputs to 3 different classes, say tiger, cat, and airplane. Then you get different predictions for each of them, and whereas the actual value will be only one of them. So then so if cat, the corresponding entry for cat is set to 1, it means that the image is definitely a cat, not a tiger or an airplane. And on the other hand, the network gives you at its output these values in the range 0 to 1. These are basically confidence values, level of confidence with which the network figures that which class the input belongs to. So in this case, the closer to 1 you are, the closer to 1 a value is, the higher the confidence level that input belongs to this class. Now to compute the error in the prediction error, the formula we use is this one over here. So what this basically does is yi is the target output, log of yi hat is the estimated output. So let's say you are in this for this particular example that you see on the right side over here, for a certain sample I, this image does not contain a tiger or an airplane. So these values yi will be 0 for that. So these entries basically go away, and only the one that has a 1 in front of it for its target value, cat, will be multiplied by the log value of what the softmax layer gave us as output, 0.7. And that will be added up for all possible, all the values in the training set. And that's how you compute the prediction, the error in prediction. So the target value of our class is 1, like it is for cat over here. And the prediction probability is 0.7. That's relatively smaller than if the target value is 1 and the prediction probability is 0.2. That would be a larger error. Now, among the metrics of quality, the one that we used in the sample code, the one that we specified was accuracy, and accuracy is defined as number of correct predictions divided by total number of predictions that were made. For a binary classification problem, that's like saying the number of true positives plus true negatives, so the ones that you got right, divided by all the number of predictions you attempted. A true positive is, for example, a COVID test can either be positive or negative. Either someone is COVID positive or not. So let's say you test somebody and that patient is actually COVID positive, and the test also says COVID positive. That's called a true positive. But a true negative is a patient is actually COVID negative, and the test also says that the patient is COVID negative. That would be a true negative. But a false positive is one where the patient is actually COVID negative, but the test says the patient has COVID, which is wrong, of course. So that kind of error is called false positive. And finally, the last possibility, where a patient is actually COVID positive, but when you test the patient, the test comes back a negative. That's the other kind of mistake, other kind of error that can be made in a binary classification problem. Other metrics are precision, which is defined as number of true positives divided by true positives plus false positives, and it is the portion of positive predictions that are actually correct. Another metric is recall, and that is should be recall over here. And recall is the portion of actual positives that were identified correctly. Now, you can then adjust for the training portion. You can adjust the number of epochs, how long you want the training to continue. You can set the number of epochs to three. Defined validation and validation data. We already did that. The output will then look something like this. You'll see in this case, the accuracy. You will see value of the loss function and accuracy after each epoch. So you can see in this case over here, the loss is gradually going down from 0.2433, 0.1184 to 0.09. Once you're satisfied with the model that you have, you can simply save all its parameters using the save weights function. You can test the model by making predictions with it, give it an image as input, and use that model that you have trained, use it to predict what the output will be. You can print out the model's predictions and check predictions against ground truth by printing out the actual label of that input. You can add more convolutional layers by just inserting a single line over here. And in order to avoid something called overfit, what you can do is you can use a technique called dropout. So occasionally you might encounter a situation where you get really high accuracy on training data. But when you use it on other data, on test data, you get low accuracy. And there is a classical sign of overfitting. And an approach to that is to use a technique called dropout, and that's easy to do. In Keras, you can just add a single line and add a single option to the 2D convolutional layer. Dropout is basically a technique, and just from this source over here, look it up if you like. Technique where you basically randomly select some neurons and you ignore them in two phases. You ignore them during training. So you ignore them during training, so you drop them out randomly. You drop out their contribution to the activation, so in the forward pass, and you also skip updating their weights on the back propagation step. And just as easily as adding a convolutional layer to an existing network, it's just as easy to add a fully connected layer using the dense option that you see over here. You can add that, and you can add specify the activation function for that. You can change the stride step size. We can select different padding methods and change activation functions just like that. And in graphical form, this kind of looks like this. So you have an input image, apply multiple filters, in this case 6 filters to it, can subsample, basically pooling or reduce the size of that you have. In this case, we seem to be reducing from 28 by 28 to 14 by 14, meaning we're using a 2 by 2 pooling filter. Apply convolutions again, subsample again, and then flatten. And after flattening, use fully connected layers between until you get to the output layer that has, in this case, 10 possible outputs. And as you can also see, typically the number of neurons keeps going down as you move towards the output. Just for information, that's an architecture for a different problem for AlexNet, something that caused the revival of interest in neural networks in 2012. This is a representation of that. It is an alternative representation of AlexNet. and uh, different parameters. And something that's actually worth seeing over here is that there's a memory utilization in different layers. So this is the input layer here at the top, output layer, softmax layer here, and in between we've got convolutional max pool, 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 and fully connected layers. And the thing to pay attention to here, why is it that the number of neurons kind of start reducing very early on? Take a look at, pay attention to the memory requirements of each layer. And that's these fields in red, 3.2 megs, 3.2 megs, then going down to 800K, 1.6 megs, 800K, 200K, 400K, 100K, 100K, down to 25K, and then down to 4K, and then just down to 1,000 parameters. 1,000 bytes. So something to pay attention, something worth paying attention to is the memory that's necessary to run the network that you're training. And here, along with it, in blue, are the number of parameters. You see that the number of parameters are actually quite small, but going up here initially, going up. And when we can get to the fully connected layers, it's these last three over here, the number of parameters suddenly jumps huge. Although we've performed pooling 2 times over here, the number of parameters in the fully connected layers is massive. It's like in the 100 millions over here, 16 million, and another 4 million in the last fully connected layer. You can probably see what would happen. You can probably try it out, maybe not even on your calculator. How many parameters would you be dealing with if these initial layers here near the beginning, where the data size is still very close to the size of the input image, how many parameters would we have there if we were not using a convolutional layer but fully connected layers instead? Okay, and that brings us to the end of this lesson, and that leaves us with just the last chapter for next time.